Centrifugal pumps are used widely throughout industry, wherever there's a need to move fluids from one place to another. To maintain them properly, you need to know how they should work, so you'll know when they're not working properly. And you need to know the most common things that go wrong, so you can recognize problems quickly and correct them before they become serious. In this program, we'll show you the fundamental operating principles of centrifugal pumps. We'll show you the major components that all centrifugal pumps have in common, and we'll show you many of the things you need to watch for so you can keep the pumps you work with operating reliably and efficiently. As you might guess from the name, a centrifugal pump works because of centrifugal force. Here's how. Let's take a blender, fill it up with water and turn it on. Notice how the water rises up toward the edge and goes down in the middle? The blades move or impel the fluid away from the center, pressing it up against the sides. The faster the impeller spins, the greater the pressure. If we opened up a hole in the side, water would squirt out harder and farther as the impeller spun faster. A real pump is fastened to a system of piping. The housing is closed. Fluid goes in the suction side and comes out on the discharge side. All centrifugal pumps work with these same basic principles and these same basic components. An impeller, fastened to the shaft of a motor, is sealed inside a pump housing. When the impeller turns fast enough to overcome the pressure or head of the fluid already in the pipes, it pushes the fluid out the discharge side of the pump. At the same time, fluid flows into the suction side of the pump. As long as the suction side is supplied with fluid, and as long as the head is no greater than the pump can overcome, the impeller keeps discharging fluid under pressure. We're going to take a closer look at each of these principles and components, because just about everything that has anything to do with keeping a pump running reliably and efficiently has something to do with one of them. We'll start with the impeller. Impellers are made from different materials and in different shapes to match particular applications. Water pump impellers, for example, are usually made of brass or bronze. Most impellers have curved blades, like this. Some have a disc or shroud on one side, while others have no shroud at all. This is called an open impeller, while this is sometimes called a semi-open impeller. When there is a disc or shroud on both sides, like this, it is a closed impeller. Many manufacturers offer replaceable impeller wear rings which can extend the life of an impeller. The old one comes off after it is worn, and the new one goes on like this. The shape of the impeller blades is important because it determines the pressure the pump will develop, the flow rate out of the pump, as well as the overall efficiency of the pump. If you replace an impeller, make sure the part numbers match, or the performance of the pump may change a lot. The motor. The motor spins the impeller. Most pumps include bearings which support and guide the impeller. Sometimes the motor and pump are coupled together by a straight shaft, while at other times a belt drive is used. In either case, correct alignment is essential if the pump is to operate reliably and efficiently. The proper alignment of offset drives and the proper alignment of direct connect couplings is an absolute necessity if you expect reliable operation. Even minor misalignment will wear out bearings, shafts, and seals very quickly. The seal. When there is a seal between the spinning shaft of the impeller and the casing of the pump, it is often a source of maintenance problems. Some seals leak because they are supposed to leak. The leaking fluid lubricates the shaft where it enters the casing. The usual trouble is adjusting the seal so it leaks at the correct rate. In addition to providing lubrication for the shaft, the seal does one of two other things. If there is more pressure inside the pump than outside the pump, then the seal must prevent the fluid from leaking out around the turning shaft. It seals the fluid in. If there is more pressure outside the pump than inside the pump, then the seal serves to keep air from leaking into the pump. It seals air out. If air is leaking into the pump, you may hear a loud rattling noise, as though there were marbles rattling around inside the pump. The sound may also be much softer. The sound you may hear is bubbles of air which have leaked into the pump. The bubbles are literally exploding under the pressure developed inside the pump. The explosions eat away at the impeller and the pump housing, causing severe damage. Correct seal maintenance not only ensures correct lubrication, it also prolongs the life of the pump by keeping out air and reducing damage from cavitation. The most common types of seals are the mechanical seal and the packing seal. A mechanical seal works by slipping one side of the seal on the shaft and the other side into the housing. As the shaft turns, these two polished surfaces are held in contact by a spring. In many applications, a mechanical seal is preferred because it seals better, and in normal service, it does not leak at all. When properly installed and maintained, it generally lasts longer. However, because the seal depends on these two surfaces being absolutely smooth, you must be very careful when installing one. The surfaces are easily damaged. In fact, a single dirty fingerprint can ruin a mechanical seal. While some small leakage may occur when a mechanical seal is first placed into service, it should leak only briefly. If the leak continues after initial startup, it's usually because the seal was improperly installed or because it was damaged in some way during installation. The pump will usually have to be torn down again and the seal replaced. The seal runs with a very thin film of fluid between the two surfaces. The fluid does two things. It provides lubrication, and it keeps the surfaces flushed free of contaminants that could damage the seal faces. To provide the correct lubrication and flushing, the pressure inside the seal chamber must be carefully controlled. If pressure is too low, contaminants may leak into the seal chamber. And if pressure is too high, the seal faces may wear out quickly. A mechanical seal is often used when the fluid being pumped can also flush and lubricate the seal. But sealing fluid may also be supplied from a clean source outside the pump. Remember, when using a mechanical seal, both the seal pressure and the flow rate must be carefully controlled in order to assure proper operation of the seal. Okay, now for a look at the other primary method of sealing a pump shaft. Packing. As the name implies, packing is material that is packed around the shaft. The packing goes into a stuffing box, which surrounds the shaft and helps hold the packing in place. The packing may be of most any material which will work with the fluid being pumped. Impregnated fabric, metal foil, Teflon, and precast rubber are a few of the more common. One of the disadvantages of a packed pump is that in order to operate satisfactorily, it must have some leakage to lubricate the seal. Either that or some other provision must be made for lubrication. Stopping the leakage on a packed pump by tightening down the gland will dry out the packing. The shaft may overheat so much that the packing will start to smoke. Damage follows quickly. Make sure you know what the leakage rate should be. Packed pumps use either a solid pack, that means packing only, or they use a sealing cage along with the packing. Now, a solid pack simply has the stuffing box filled with packing. A solid pack is normally used when a slight liquid leak will lubricate the packing adequately. When more lubrication and cooling are required, a sealing cage or lantern ring is used. The lantern ring serves as a point in the middle of the packing where fluid can be put in or taken out. Fluid put into the sealing cage under pressure provides the necessary lubrication as well as seals out the outside air. Taking fluid out can help cool the packing as well as the shaft. Fluid usually goes into the cage through a tapped hole, so it's important to make sure the sealing cage is directly under the hole when repacking a stuffing box. Just as with a mechanical seal, the fluid pressure in the stuffing box must be carefully controlled. Too much pressure may loosen the packing or cause the lubricant to contaminate the product being pumped. Too little pressure may allow contaminants to leak in, dislodge or damage the packing, and damage the shaft. The pressurized fluid injected into the sealing cage may come from an external source, in which case the seal is called an external seal. When the fluid to the sealing cage comes from the high-pressure side of the pump, then it's called an internal seal. Internal seals are normally used when pumping clean, cool water. When pumping gritty or corrosive fluids, there should be an external seal with a cool, clean liquid supplied to the stuffing box. Now, a pump seal, whether it's packed or has a mechanical seal, must ride on the pump shaft as the shaft turns, so the shaft is subject to a lot of wear. On larger pumps, and especially those that use packing, it's likely the shaft will have a shaft sleeve. This is a cylinder of machined metal which screws onto the shaft and provides a wearing surface at the point where the packing rubs. If necessary, it can be hardened. If it becomes grooved, scored, or cracked from wear, then just the sleeve will have to be replaced, not the whole shaft. One other kind of seal you may encounter is commonly called a dynamic seal. Pumps that use this kind of seal have an extra impeller on the shaft which forces fluid back toward the main impeller. As long as the pump is operating, this impeller keeps fluid from ever reaching a small mechanical seal, here, which seals the pump when it's stopped. Now, there is another kind of centrifugal pump which does not require a seal at all. Instead, the link between the shaft of the motor and the impeller in the pump is magnetic. It's often called a mag drive pump. A mag drive will usually have a magnetic cup coupled to the motor. The cup surrounds a housing which holds the impeller in place as it spins. Since no shaft goes through the body of the pump, there is no need for a shaft seal. These pumps do not leak at all because nothing penetrates the pump casing. The casing. The casing, or housing of the pump, is frequently made of cast iron, steel, or bronze, so it's strong enough to withstand the pressures developed by the pump. This part of the casing, the volute, provides an easy path for the liquid to reach the discharge outlet. Many larger pumps, and especially those handling gritty material, have wear rings in the casing and on the impeller. Wear rings are replaceable, so that when wear occurs, just the ring, not the whole casing, has to be replaced. The proper wear ring clearances are specified by the manufacturer. You must maintain these specific clearances when replacing the rings, or the pressure, flow rate, and efficiency of the pump will all change. The discharge side. The discharge side is the business end of the pump. Often, pumps are rated based on how much fluid they can discharge per minute at specific speeds. In practice, how much they can pump depends on three main factors: the speed at which the pump is driven, the size of the impeller, and the head in the system. Head means how much work the pump has to do. On the discharge side, that means how much fluid the pump has to push out of the way before it can discharge the fluid in the casing. For example, according to its specifications, this pump, when driven by a 1.5 horsepower motor, will pump 96 gallons of water per minute if the pipe is 10 feet long and filled with water. If the pipe is 30 feet long and filled with water, the pump will still deliver 78 gallons per minute. But at twice that length, at 60 feet, the pump will deliver only 17 gallons per minute. As the pump has to do more and more work to move this head of fluid away, it takes it longer and longer to produce a given amount of fluid at the end of the discharge side. That's why pumps have to be matched to their application. And it's why changes in the pump, changes from wear or leaks or setting the wrong clearances or installing the wrong parts, can affect the operation of an entire system. The suction side. There are two things to consider on the suction side. The first is priming, and the second is suction. We'll look at priming first. A pump that is primed is full of fluid on the suction side. This is critical to the operation of a centrifugal pump because without fluid on the suction side, the impeller turns in air. There is no way the water down here is going to jump up here into the pump. But if the line is full of fluid, if it's primed, then starting the pump will discharge fluid under pressure, and fluid can be pushed in the suction side into the low pressure area created as fluid is discharged. One common way of keeping a pump primed so it will start properly is to install a check valve in the suction line. It's got a flapper in it, and it allows free flow in one direction only. Fluid can come up the suction line, but it can't go back down. So when the pump is turned off, the line stays full of fluid, ready for the next time it's started. When a check valve is installed on the end of the suction line, it's called a foot valve. As long as a check valve or foot valve works the way it should, that is, as long as it keeps the suction side full of fluid, then the pump will start reliably. However, if the valve leaks because of damage or debris, then the pump will have to be reprimed before it's restarted. Some pump installations do not need check valves or foot valves because they have flooded suction. This means the level of the fluid on the suction side is above the pump, like this. The suction side is always primed. Whether a pump has flooded suction like this with a fluid supply above the pump, or whether it must provide suction lift like this with a fluid supply below the pump, may have a large effect on the pump's output. For example, if the distance between the top of the reservoir and the pump is 10 feet, then the work the pump must do to move the fluid is reduced because the pressure of the water is already trying to force fluid through the pump. If the pump could deliver 78 gallons per minute with a 30-foot head, then the same pump with a flooded suction of 10 feet above it will have its head, the work it must do, reduced by 10 feet. The pump head is reduced to 20 feet, and it can now deliver 86 gallons per minute. But if the pump must raise the water up 10 feet in order to get it to the pump, then the work the pump must do is greater. So the head increases from 30 feet to 40 feet, and the pump output drops from 86 gallons per minute with flooded suction to 58 gallons per minute with suction lift. To maintain the correct head and flow rate, it is important that the suction line be as large or larger than the discharge line, that it have as few loops, bends, and fittings as possible, and that it be as short as possible. If a suction line strainer is used in the reservoir, it should have an area several times as large as the cross-section of the line, and it must be kept clean and free of any obstructions. Finally, any valves on the line should be wide open during operation. In this program, we've seen how centrifugal pumps work, and we've taken a close look at those parts of a pump which may require routine maintenance. In addition, we've seen some of the reasons why that maintenance may be required. The better you understand how pumps work, and the more you know about the pumps you work with, the better you'll be able to keep them running reliably and efficiently.